Okay, so Junior Roberts here. So we're going to be looking at this question as we prepare for the CSEC Physics Exam. So let's go right into this question. So it says here that this question is about some of the physical principles involved in scuba diving. Scuba divers breathe air from steel tanks carried on their backs. The tanks contain air at a pressure of 2 times 10 to the 7 pascals. At atmospheric pressure, this air would occupy a volume of 2.5 cubic meters. Now, the first thing that we want to do with this question is we want to explain in terms of the kinetic theory of gases how the air exerts a pressure on the insides of the steel tank. So, to begin this question, we have to remind ourselves about the kinetic theory of gases, right? So, with the kinetic theory of gases, what we can consider is the fact that a gas is made up of many tiny particles. Right now, the kinetic theory of gas is related to the kinetic theory of matter, right? So a gas is made up of many tiny particles, right? And these tiny particles are in a state of motion, right? Random motion. Now, when we have gas enclosed in a container, let us say we have a container like this, right? And we have gas molecules, right? These gas molecules, they have a lot of space and they can move about freely, right? They move about in all directions freely, right? Random direction, like this. Now, due to this random motion, right, they're going to be colliding with each other and also colliding with the walls of the container. Now, due to these collisions, though, we're going to get a force being exerted on the walls of the container. And that force now will actually produce a pressure. So we're going to say now that gases are made up of tiny particles in constant random motion, right? This results in the gas molecules colliding with the walls of its container. In this case, we could mention the steel tank, walls of the steel tank, right? These collisions cause a force to be exerted over a particular area. Which results in a pressure, right, inside the steel tank. Right? So because of the collisions with the walls of the steel tank, right, we get a pressure being exerted on the walls of the steel tank. So now we can continue. Next thing now, we also want to explain why the pressure in the tank increases when the tank is left out in the sun. So for this one now, we can say now that as a result of the tank being in the sun, right, what we're going to get is that the temperature of the gas inside the tank will increase, right? And this increase in temperature causes the gas molecules to increase their kinetic energy, right? Thus colliding with the walls of the container harder, and this increases the pressure, right? So increasing the pressure. So what we're seeing with this one is when the steel tank is in the sun, the sun is going to actually heat up the steel tank. Now, the gas that is trapped inside the steel tank will also heat up, right? Now, because the gas would have heat up, its temperature will increase. Now, we can remember that temperature is just a measure of the average kinetic energy. So if the temperature increases, the average kinetic energy of the gas molecules must increase. So therefore, the gas molecules are going to be moving about faster. So they're going to collide with the walls of the container harder and more frequently. And therefore, now that's going to increase the pressure. Now, next question now says that we are to state why the pressure in the tank decreases as air is released. So for this now, what we can say is that when we release some of the air inside the tank, what's going to happen is that we're going to have less gas molecules. Now, due to this reduction in the number of gas molecules, we're going to have the number of collisions being less. So as a result of that, the pressure will reduce. So we're going to say now that as air is let out, the number of gas molecules reduces, thus decreasing the number of collisions, right? Therefore, the pressure decreases, right? So that's what we're going to say for that. So now, next question now says that we're to determine the volume of the air when inside the tank at a pressure of 2 times 10 to the 7 pascals. So what they want us to do essentially is to determine the volume of air inside the tank when the pressure is 2 times 10 to the 7 pascals. So now, if we go back up to the question, we see we're told that, okay, at a pressure of 2 times 10 to the 7 pascals is what the pressure would be inside the steel tank. So what they're saying is that at atmospheric pressure, this air would occupy a volume of 2.5 cubic meters. So therefore now, what we can consider in this case, we can consider that, okay, we have the pressure right here at 2 times 10 to the 7 pascals. We are told that at atmospheric pressure, the volume would be 2.5 cubic meters, right? So now, what we can consider in this case, we can consider Boyle's law, right? We can consider Boyle's law, which relates the pressure to the volume. So what we can write, first of all, is we can write that P1 V1 is equal to P2 V2. Now, in our case, P1 is, let us say P1 is atmospheric pressure. Now, we're given that atmospheric pressure is 1 times 10 to the 5 pascals. So we're going to say that P is equal to 1 times 10 to the 5 pascals. V1 is equal to, because we're told that at atmospheric pressure, the air would occupy a volume of 2.5 cubic meters. So we're going to say V1 is 2.5 cubic meters. P2 now is equal to 2 times 10 to the 7 pascals. So we say 2 times 10 to the 7 pascals, and then V2 now would be our unknown. So now, since we're trying to find V2, we can make V2 the subject. When we do that, we're going to get V2 is equal to P1 V1 divided by P2. So what we do, we just divide both sides by P2 and we get our expression right here. So V2 then now is going to equal to P1, which is 1 times 10 to the 5 pascals multiplied by V1, which is 2.5 cubic meters, and P2 is 2 times 10 to the 7 pascals. Now, due to the limited space, I'm just going to enter this directly into the calculator. So taking the calculator, right, we just simply say, so with the calculator here, we're going to say 1 times 10 to the 5 multiplied by 2.5 equals, right, 250,000. Then we say divide now by 2 times 10 to the 7 pascals, and we get 0. So we get 0.0125 cubic meters. All right, and that would be our answer. Now, next question says that when the tank is in the sun, the temperature of the air inside reaches 40 degrees Celsius, and its pressure is 2.1 times 10 to the 7 pascals. Under the water, the temperature of this air goes down to 10 degrees Celsius. Assuming that the volume of the tank does not change when it is underwater, determine the pressure of the air in the tank when it is underwater. So now, in this case, right, we are given the temperature of the tank when it is in the sun and its pressure, right? And then when it goes underwater now, the temperature goes down to 10 degrees Celsius, and we want to find out, okay, what is the pressure of the air in the tank when it is underwater? And we're told that the volume is kept constant, right? So the volume of the tank does not change. So once we have volume being constant, we're going to be considering the pressure law. Now from the pressure law, we can write that P1 over T1 is equal to P2 over T2. Now in our case, P1, let's say P1 is this pressure right here, so 2.1 times 10 to the 7 pascals. T1 now is going to be the temperature when it is in the sun, which is 40 degrees Celsius. So we have 40 degrees Celsius here. But because we're dealing with the gas laws, we have to convert to Kelvin. So we're going to add 273, and this works out to be 313 Kelvin. All right? Now, P2 is our unknown, and T2 now is going to be 10 degrees Celsius. So we have 10 degrees Celsius plus 273, which works out to be 283 Kelvin. So now, we're trying to find P2, so we're going to make P2 the subject. When we do that, we're going to get P2 is equal to P1 times T2 divided by T1. So now it's just a matter of us substituting the values. So P1 is 2.1 times 10 to the 7 pascals multiplied by T2, which is 283, right, divided by T1, which is 313 Kelvin. So now, after doing the calculation, we're going to see that P2 is equal to, so let me get the calculator. So for this one now, we say 2.1 times 10 to the 7 multiplied by 283 equals divided by 313, right? And we get an answer of, we're going to write this to two significant figures, so we're going to get an answer of 1.9 times 10 to the 1, 2, 3, 4, 5, 6, 7 to the 7 pascals. Right? And that would be our answer. So now, next question says we're to express the change in air pressure when the tank is underwater as a percentage of the air pressure when the tank is in the sun. So now, since the pressure when the tank was in the sun is 2.1 times 10 to the 7 pascals, and the pressure in the tank when the tank is underwater is 1.9 times 10 to the 7, and since we want to express the change in temperature as a percentage, first thing we're going to do, we're going to find the change in temperature. So we're going to find delta P, which is P2, well, P1 minus P2. All right, so this works out to be supposed to be P1. So we say P1 minus P2, right? So we take the smaller from the larger, so we're going to have 2.1 times 10 to the 7 pascals minus 1.9 times 10 to the 7 pascals. This one is going to work out to, so we have 2.1 minus 1.9, that's going to be 2 times 10 to the 7 pascals. And since they want us to express it as a percentage, what we're going to say is that we're going to say, because we want to find a percentage of the, so express the change in pressure when the tank is underwater as a percentage of the air pressure when the tank is in the sun. So we're going to say now 2 times 10 to the 7 pascals divided now by the pressure when the tank was in the sun, which is 2.1 times 10 to the 7 pascals multiplied by 100. So now, when we do our calculation, so let's grab the calculator. So we say 2 expressed to the 7 divided by, it should be 0.2 right here, right? Back up a bit, should be 0.2. So 0.2. So therefore this is 0.2 right here. So now, taking the calculator, right, we say 0.2 divided by 2.1. Alright, so 0.2 expressed to the 7 divided by 2.1 expressed to the 7, right? And we're going to get 0.095, so we can multiply that by 100 now. Right, and we're going to get 9.5%. Right, so the difference in pressure is 9.5%. Right, and that would be that question. Next one now says that because of increasing pressure with depth underwater, there is a limit to the depth to which a scuba diver can safely go. Calculate the total pressure exerted on the diver who is 20 meters under the surface. So now, for this, right, since we're trying to find the total pressure exerted on the diver who is 20 meters beneath the surface, we need to say now that the total pressure, let us say, total pressure exerted on the diver, right, will be due to the atmospheric pressure, plus the fluid pressure, right, or the pressure due to the water. So now, the first thing we're going to do now, we're going to find the fluid pressure. Let us say fluid pressure, P, is going to be equal to rho GH, where rho is the density of the fluid, which is given right here as 1 times 10 to the 3 kilogram per cubic meter. G is the gravitational field strength, which is 10 newtons per kilogram, and H is the depth, right, which is given as 24 meters. Right, so this is 24 meters. So now we can now plug in the values and do our calculation. So we're going to have rho being 1 times 10 to the 3 kilogram per cubic meter multiplied by G, which is 10 newtons per kilogram, multiplied by the depth, which is 24 meters. Now, plugging these into the calculator quickly. right? We say 1 times 10 to the 3 multiplied by 10 multiplied by 24, and we get an answer of 240 pascals, right? Pascals, which is the same thing, right, as 2.4 times 10 to the 5 pascals. So we just move our decimal point 1, 2, 3, 4, 5. So we get 2.4 times 10 to the 5 pascals. Now the total pressure now. So the total pressure, right, will simply be the pressure of the atmosphere, which is given right here as 1 times 10 to the 5. So it's given right here as 1 times 10 to the 5. So we say 1 times 10 to the 5 pascals plus 2.4 times 10 to the 5 pascals. So now, adding these together, now we're going to say 1 plus 2.4 is going to give us 3.4 times 10 to the 5 pascals. And that would be our question here. So again, Junior Roberts, if there was anything in this video that you wish to get further clarification on, you can post it below in comments and I'll do my best to clear up any misconceptions. Like this video if it was helpful. Click subscribe on the bell so you're notified whenever I post new videos like this. Thank you for watching.